So I'm just having a little play about today with VBE multipliers. Now, if you have a audio amplifier output stage, a standard linear class B, if you're using bipolar junction transistors in any configuration or vertical MOSFETs, aside from a self-biasing class A type output, you need to track the temperature of the output stage and compensate for drifts in output current, the quiescent current, relative to the temperature the output stage has got to. And to do that, we use what's called a VBE multiplier or amplified diode circuit. VBE stands for voltage base to emitter. So the basic idea is, just focus in on that, is simply you get a small signal transistor. Come on, there we got something to focus on now. Right, so let's say we've got our constant current sink, and up here we've got our voltage amplifier stage from our input stage. So let's say we're drawing 10 milliamps through here. Now what happens is, obviously like any transistor, you need about 0.65 volts between the base and emitter junction to turn it on. So what you can do, let's say, obviously you'd normally make this adjustable. I'm just keeping it simple here. So this lower resistor here is going to have 0.6 volts across it. So if this was, for instance, 100 ohms, and you had 1 kilo ohm up here, at whatever point this transistor turns on, it will start to conduct. Well, so we've got 0.65 across here. Well, obviously, in order to turn it on, we have to generate 0.65 volts across this lower resistor. So that's going to require a certain amount of current, and seeing as this resistor is 10 times bigger, it's going to need 10 times a voltage drop across it. So in this instance, this would be 6.5 volts. So the 6.5 will combine with the 0.65 to give about 7.15 volts or so. Obviously, it's open to natural variations in the transistor, and obviously it's temperature dependent. Hence the reason we're using the circuit. Obviously, you'd normally make this point, you normally make it an adjustable setting, but obviously if you was having 7.15 volts, you'd probably be using this on a MOSFET output stage, but this is the reason why I'm actually making this video. Now, if you look here, I have two near identical circuits. They're both being fed from a constant current source of 10 milliamps. And if you look at these 2 meters, you can see one of the transistors has, drop my pen, has 3.72 volts across it, and one has 7.25. The only difference being between the two circuits is the transistor with the lower voltage across it, the actual whole multiplier is generating near identical amount of bias, but I just have an additional resistor here, which is then generating sort of 3.5 volts or so across it, 3.3, whatever it worked out to. So in order to allow me to do that, the two circuits I have both have a 1 kilo ohm resistor at the top half, but the transistor with the 3.72 volts across it, this lower resistor here is 220 ohms. So as you can see, 220 ohms, it's 0.65 volt is only going to require less than half the current to generate that 0.65 volts, and obviously the base will conduct. Now obviously this will never get higher than that, because once the base conducts, this transistor starts to conduct, the voltage across it is pulled down to the point where it's always held just at the point of being turned on, turned off. It's in its forward operating region. Now, like the output transistors, we're trying to track like diodes, normal diodes, not Zener diodes. As the temperature across it rises, the voltage across this junction here will decrease. And so obviously the voltage at the output is always the addition of the voltage here and the voltage here needed to generate the amount of current that creates a 0.65 volts across it. It's a standard potential divider network. Obviously you just have a slight differing voltage. The two values of resistor stay the same. Now obviously the higher the ratio between these two transistors, you can see it has a greater effect on the voltage overall on the transistor circuit, because for instance if this is 10 times bigger, then if this drops by 0.1 volts, this has to drop by a whole volt. If these two were the exact same, actually drop by 1.1 volt, it's potential divider, so it's by 11. But if these two were the same value, then I'd have to start off with 0.65 volts across here, 0.65 volts across here. If I heated this transistor up, so this only had half a volt across it to turn the base on, there's obviously a half a volt across there. So as you can see, the whole voltage output from that would only drop by about, well, it's 0.65 plus 0.65 is 1.3, so it would only drop by 0.3. If I did the same with resistor, the 1K and the 100 ohm, well, 0.5 across here would be 5 volts across here, so it would be 5.5. I'd have lost like 2 point something volts, 2.15 in. You can see this is actually generating 7.25. There's natural differences. So now, when you're using like a bipolar junction transistor output stage, obviously, especially in a complementary feedback pair, you'll only be generating 1.2 volts across this transistor. So obviously you'd have a fixed resistive element in the top half, you'd put a resistor in your lower half, and what you actually do is, if I redraw it, we'd say we've got same again standard N-type transistor. We obviously have to put the resistor in the top half. Oh, that's scratchy. So by putting the potentiometer in here, if you notice we put the wiper connected to the bottom. So if the wiper goes open circuit, I've done that the wrong way around. Oh dear. Hang on, let me just pause you and redraw this. Right, there we are, back again. So as you can see, we have pretty much a similar circuit. We've just increased the value of the lower resistor here a bit. So obviously the value of this resistor limits the amount we can turn the circuit off or on. If we shorted that out, we'd never be able to turn the VB multiplier on, because we'd never be able to generate the base voltage. If we have a really large one, then obviously there's only so much potential divider we can adjust out with these values here. So it would only be able to turn off so much. It would only generate a very small voltage across it. By putting the wiper arrangement on the potentiometer like this, if the wiper goes open circuit, obviously we'd have it adjusted as you want to increase your bias. You're winding the resistance down. You're winding basically the taper closer and closer to this junction on the potentiometer. If the potentiometer wiper goes open circuit through dirt or corrosion like happens, basically all of a sudden you end up with this two potential divide. These resistors are basically in series forming one resistor, and then obviously you have this is a direct connection here. So the VB multiplier will clamp off. The output stage will suffer severe crossover distortion and stuff. It'll sound terrible. It won't be biased on anymore. If we did it this way round, the incorrect way, obviously if this went open circuit, there's very little anyway current being supplied to turn this resistor, to generate voltage on across this resistor and turn the transistor on. So the voltage across the transistor will soar right up, and the output stage could go into full-on Class A thermal runaway and destruct quite rapidly. It could take minutes, it could happen within seconds. So we always do it like this. Anyway, that's the basic overview of it. I've tried to stay out of the maths. you know, like this massive, it's just your basic potential divider circuit, R1 plus R2 over R2, you know, with your voltages put in to give you your voltage output. So yeah, that's the basic schematic layout of what's going on here. Right, so here's the basic layout. So we've got our constant current source. There's two of those. They're obviously feeding into these transistors. So at room temperature, we can see one of them with the low voltage on is at 3.57, and the one with the higher voltage on is 6.91. It's just, as you can see, it's just cycling between the two. So let's drop to 3.56 now. Actually, 3.56 and 6.9. We'll call it 6.91. We'll put an R there for room temperature. So turn my soldering iron on to get that warmed up. So first of all, I've got some Aero Clean spray. This stuff boils at a very low temperature. If you spray it on a piece of metal, once it boils off, you can see frost from water vapour in the air that's frozen onto the metal. So if I spray a bit on each of these transistors, it should cool them down. Okay, you can see they're wet. That one less wet than the other one, so let's give them another little blast. So you can see whilst they're wet and cold, 3.79 and 7.27. 3.79 and 7.27. So that is cold. Okay, so as you can see, as they're starting to warm up, the voltage across them is starting to drop back down again. So, you know, once they get back to room temperature today, it says is about 15.8 degrees in here. Okay. Checking my batteries, I've got all these leads flying around. Anyway, I went downstairs to put the kettle on. I was downstairs for a few minutes just looking at some stuff on my phone. Come back up here and it smelt of burning, and these leads had shorted out, and these batteries had got so hot you couldn't touch them. Yeah, they've cooled down now. That's lucky, really. That yeah, they'd have vented nicely anyway. They should fail safely. By the way, look, Maplin, I actually brought them today. Everything in the sale. I spent quite a chunk of money at Maplin today buying some bits and bobs. It's be a shame to see it go. You know, it couldn't compete with the other electronics suppliers, but it was handy having it just across town if I was building something and I just wanted to nip out and get a few bits. Obviously, they had very limited stock, but you can normally adjust the design you're making to work with the components you have available. So yes, I don't know whether they will continue online, but obviously if I'm going to buy stuff online, I'm just going to use one of the, you know, larger electronics wholesalers with the big supply and the exact bits I want. So yes, is a shame, but I picked up a new soldering iron. I've got a couple of Antex ones up there, 25 watts. I might do a review on this actually, because it's a 40 watt iron, but it's got a real, it's their cheapest one. It's got a real big solid tip on it. It's got a good thermal mass. I think I might do a review explaining why that's good another day. But yeah, it's just to say it's a very good iron actually. It's a cheap iron. I brought various bits for it. I've had a look on eBay, and this element configuration is fairly standard, should be able to replace it, but saying that, it looks like it could be a nice long life element anyway. It's a big element, so who knows, I might never have to replace it. Anyway, I'll get that warmed up a bit and we'll warm these transistors up and see what effect it has on them. Okay, so 3.57, 6.93, you can see we're just about back to room temperature on these transistors now. So I'm going to try and warm up one for about 5 seconds. The clock on my phone screen is running, so when it hits 30... 6.49 that had dropped down to, so we'll make a note of that. 6.49, and that was hot. Obviously, I know it's not the most scientific way of doing it. It's not calibrated to exact temperatures, but you know, it gives us an idea of how they respond. So we'll try and do the same again on this one. Okay, 3.35 that one dropped down to. So let me write that down. I shall do the maths off camera because I was on nights last week and my brain is not working properly. Right, so as you can see, the transistor with the lower initial voltage across it, because obviously the upper and lower resistor, the ratio between them is lower, the overall gain of the stage is lower. What it amplifies, obviously, it's your simple potential divider network. So as you can see, when we cooled it down with spray, it decreased by 0.21 volts. When we warmed it up with the soldering iron, it increased, when we warmed it up with the soldering iron, it decreased by 0.21 volts, and when we cooled it down with spray, it increased by 0.23 volts. Whereas the transistor with the higher voltage across it, when we heated it up with the soldering iron, it decreased by 0.42 volts, so twice the value of this one. And when we cooled it down with the spray, it increased by 0.36 volts. So obviously, like I say, it's not perfectly scientific, but as the ratio between the two is nearly double, you'd expect to see about twice the temperature coefficient compared to this one. So if we'd done it under proper conditions, if I'd had the two transistors actually firmly bonded to a heatsink, I could have, we could have made sure that the transistors changed in temperature relative to each other at the same amount, and then these results would have been a little bit more repeatable and acceptable. But it's just to show you the general idea of what's going on here. So the reason I'm looking into this is the amplifier I'm currently working on. I use vertical MOSFET output stage. Well, they're going to need somewhere around the 7 volt range to bias them on. So if I just used the single transistor, high value resistor off the collector, low value off the emitter, and then a potentiometer here, I could generate the voltage easily. But as the amplifier starts to warm up, if I start to drive it hard, the temperature compensation will overcompensate. It'll push it out of class B. If it got quite hot, it would go well into class C. Distortion would go through the roof. It would sound terrible. It could damage the tweeters, because obviously when you get crossover distortion, there's a lot of high frequency artifacts and stuff. So all in all, it's also just bad design. You should be able to compensate for variations in temperature quite accurately. You shouldn't have to face a compromise like that. So what I'm going to do is, I think if we redraw the, who's here? Just me. If I redraw the circuit again, what I should do is, there's my voltage amplifier stage. Should have put my potentiometer in, really, shouldn't I? Oh, dearie me. Hey, look, I was on nights last week. Anyway, you get the idea. So that's my potentiometer. I can adjust there. And I might put, say, a 1 kilo ohm potentiometer in here. Should have drawn that one in as well, shouldn't I? What I can do is then adjust that. So I can adjust the resistance in the collector circuit here. So if my stage is running about 6 milliamps, so if I had a 1 kilo ohm potentiometer here at full adjustment, I'd have 6 volts across here, and then I'd maybe only have to adjust this for 1 volt, 1.5 volts, and likewise I could completely down this so there's 0 volts across it, and I'd have to adjust this to generate all the voltage. So I can bond a small transistor like a IRF540 or something to a heatsink and one of the MOSFETs. Well, 2 of them really. I could do 2 of them just dissipating power and trying to maintain a relatively accurate voltage to temperature difference between the 2 of them. It doesn't have to track, do you know what I mean? A few millivolts here and there isn't going to matter. But by doing this, I can get an idea. Rather than, I don't want a potentiometer I have to put in every circuit. It's a never failure node. So I can get an idea of where's a good value and just replace it with a solid static resistor. I'm going to say it's probably going to work out somewhere between the 470 to 560 ohm mark. But yeah, that's the basic principle anyway. If you was wondering what the red LED was on this circuit, you can see there's a couple of transistors that aren't the ones I was playing about with. Those are part of the constant current source. If you look at an LED, if you increase its forward voltage, it'll suddenly reach a point, like any semiconductor, it'll start to conduct, and then it starts to, you know, its internal resistance becomes very low and it starts to conduct with very little change in voltage, current-driven devices. So LEDs lend themselves quite readily to being a good voltage source for constructing a simple constant current source around. So basic circuit here, 18 volts from our two batteries, LED, resistor just drawing a few milliamps of current. Gives about 1.6 volts to turn this red LED on, it measured. So the transistor dropped about 0.6 volts from base to emitter. So it left a volt across the emitter resistor. So whatever resistor we put in there will have 1 volt across it. Well, Ohm's law says current is voltage over resistance. So 1 over 100 equals 0.01 amps or 10 milliamps. So my VBE multiplier was just in here. So the few tens of millivolts it changed as I was changing the temperature of the transistors, I knew had very little effect on the current through it, because obviously, you know, I wanted to purely measure what effect the transistor is solely having on the voltage being generated across it without trying to factor in changes in current through the transistor and through the bias network. So yeah, this is, you know, this is actually quite a good constant current source as they go. It's used in many amplifiers and stuff. It lends itself good up to, you know, maybe 100 kilohertz or so. Voltage swings of sort of 50-60 volts have very little effect on it, as long as you don't go outside of the range needed for the transistor to still operate in minimum sort of collector to emitter voltage. It can be expanded on. You can put a second transistor in here on, you know, you put in like multiple resistor networks. That way you multiply. Obviously you've already got a very high resistance here because you've got the output of this collector, the maths on it is, it's something like you have to take the hybrid forward output conductance, whatever it is, yeah, you add that onto the value of the gain of the transistor times the emitter resistor, and that gives you the output impedance on the collector. So if you've already got, you know, several hundred kilo ohms equivalent AC dynamic resistance due to the isolation effect of this resistor by the base emitter junction, you've then put a second one in here with leaving just a few volts across that. Well, that then becomes the value of your tail resistor. So it's then, instead of just being 100 ohms, it's then like several hundred kilo ohms times by the forward gain of the transistor. So, you know, you can end up with current sources or sinks. You just reverse it for a current sink, use N-type transistors and flip them over. You can very easily get a constant current source that will supply tens of mega ohms of dynamic AC output resistance. So, handy little circuit. Yeah. So, and that's what the little LED and these transistors and stuff was on here anyway.